All right. So Professor Caroline Trotter is a professor of global health at the University of Cambridge and the director of Cambridge Africa. Cambridge Africa is a university program that supports African researchers and promotes mutually beneficial collaborations and equitable partnerships between Africa and Cambridge. Her research focuses on the epidemiology of vaccine preventable diseases. She has collaborated widely with colleagues across the African meningitis belt to study the epidemiology and control of epidemic meningitis. She's a member of the World Health Organization Technical Task Force for Defeating Meningitis by 2013. Ladies and gentlemen, Professor Caroline Trotter. Please put your hands together for her.
Okay, I'm afraid I can't hear anyone at your end. I wonder if you can hear me. Okay, apparently you can hear me. I just can't hear you. So I will start sharing my screen. I think we'll have to think of a different way of for the question and answer session. So I'll just share my screen. So I'm Caroline Trotter. I'm the director of the Cambridge Africa programme, and it's a pleasure to join you today. I'm going to tell you a bit about Cambridge Africa and some of the opportunities there might be for you within the Cambridge Africa programme. So first of all, to say what Cambridge Africa is. Cambridge Africa is a university programme that supports African researchers and promotes mutually beneficial collaborations and equitable partnerships between Cambridge and African universities and research institutions. So we cover all subjects across the University of Cambridge and the sort of allied institutions. We're not just interested in chemistry, even if that's what the audience is today. So we have a broad programme across different topics. But we do aim to provide support to African researchers. And I'll say a bit more about how we do that. We do this in four main ways, really. We have schemes that help to build new collaborations and strengthen existing collaborations. And we're really emphasising the sort of mutual benefit from collaborations between Cambridge researchers in Cambridge and in Africa. I'll tell you a bit more about one of the schemes that underpins this. In the second pillar, we provide an enabling academic environment for African early career researchers. This might be students who are based in Cambridge, or sometimes students who are based in in African universities, or early career researchers, postdocs in African universities, and we welcome them to collaborate and access some of Cambridge's facilities. We encourage and facilitate networking, really important. particularly for early career researchers, to expand your network, and having networks in different countries can be really valuable. And we support training activities for institutional research support teams, particularly research management support, so that the PIs can carry on with their research and have good support on the administration and coordination side. And really today I'm going to be concentrating on these first two pillars and highlighting some of the opportunities there are for African researchers and students in Cambridge. And just to emphasise that the ethos of the programme and its partnerships are based on equity, transparency and trust. We are not based on an extractive model. We really are here to support African researchers. And in that regard, activities should be driven by the needs identified by African partners in order to address African priorities and African research priorities. So one of our key schemes is the Cambridge Africa Albarada Research Fund. This was established 11 years ago in 2012 with generous support from the Albarada Trust. And the aim of this is to really encourage joint working between Cambridge and Africa. The fund supports pairs of researchers at postdoctoral level and above from the University of Cambridge, or potentially allied institutions in the area, like the Wellcome Trust Sanger Institute, and sub-Saharan African institutions across all disciplines to initiate and or strengthen research collaborations. And we're very proud that to date 300 awards have been made, which enables this interaction between Cambridge researchers and colleagues from African universities and research institutes. And we have projects, as you see from this map, from 31 African countries. There's concentration, you can see by the colours in some areas, but we are keen to work across sub-Saharan Africa. So this is an opportunity that may apply to some of you listening. To be eligible for an Albarada Research Award, you must have a PhD. You must have an appointment at an African university or research institute, and you must identify a Cambridge co-PI. So really the programme is based on this being a partnership between Cambridge and Africa. So we have these system of having joint PIs between two institutions. I'll just pause a little bit and suggest how you might identify Cambridge PI if you think, oh, this is really interesting. I know that there's work in Cambridge that's really exciting, and I want to get involved in this, or there's some equipment in Cambridge that I'd really like to be able to use. Well, then you need to identify the Cambridge PI. We have some tools that can help you with this on our Cambridge Africa website. We have a researchers database, and you can search here for individuals with shared interests. And these are people who have already identified as sort of friends of the Cambridge Africa programme, if you like. If you can't find anyone in your database, you can also search the department or faculty that's aligned with your interest. Every department has decent websites now. And you can also then write to the Albarada coordinator, and we can introduce you to the potential collaborator. We have different types of grants through the Albarada Research Fund. We have travel awards of £3,000. This is really just to sort of initiate a new relationship between a Cambridge PI and an African PI. We have workshop awards. If you have some training that you wish to carry out, or other forms of workshops, you can apply for awards of between £5,000 and exceptionally up to £10,000. Our main award really is this collaborative research grant, where you can apply for up to £20,000, and this is really intended as a catalyst grant. It's enough to get you started, and if it goes well, you will have enough evidence to be able to apply for bigger grants. And we also have equipment grants where there's an existing collaboration. The equipment can be purchased for use in the African University or Research Institute. Again, that's a maximum of £20,000. We are just about to open our call for 2023. next week on the 5th of June. And we have this 3-month window which allows you to identify potential collaborator and then co-create the research project. And it's really this period is quite important to make sure that it's a genuine collaboration, particularly where there are there's a new idea or a new collaboration. It gives you time to develop the project jointly. There's more information on the Alvarado Research Fund on the website, and I'll give them the link below. Just to highlight, as well as our standard Alvarado Award round, which we run once a year, we were able to run a COVID emergency award scheme, and we made 16 awards, 16 projects in 10 countries. And these were quite diverse, from looking at immunity to COVID, to looking at the impact of school closures, and social media, the social media responses to COVID, and a whole range of different elements. We supported diagnostics, enhanced diagnostics in DRC and Madagascar. We have a report on what was achieved by these emergency awards that I can direct you to from on the website as well. Some of you at an earlier stage, before you've commenced your PhD, might be interested in scholarships. David Izugu is a Cambridge Africa PhD scholar, now completed, and these PhD scholarships were supported by the Cambridge Trust and the University of Cambridge. 5 scholars each year were recruited from sub-Saharan Africa across all subjects, and the 7th and last cohort entered in 2021. So we had 35 Cambridge Africa PhD scholars, of whom David is a shining example. The Cambridge Trust is now continuing this scheme, but under another name, and will continue to offer 5 PhD scholarships to candidates from sub-Saharan Africa for the next 8 years, which is great news. The new scheme is called the Changemakers Scholarship, and this is a program of full cost scholarships for PhD students. Again, it's any subject and open to candidates, actually any country in Africa rather than restricted to sub-Saharan Africa. And it aims to provide support to talented students who require assistance to take up their place at the university. This is closely aligned with the MasterCard Foundation Scholars Programme that I'm going to be talking about in a moment. And the priority will be given to students whose research contributes to the development of the continent and to climate resilient and sustainable futures for Africa and the world. And so there's a slightly different emphasis for these new scholarships, which were awarded for the first time in 2022 and will continue for 2030. There are other opportunities for PhD scholarships in Cambridge. I've only mentioned 5, and when you consider the size of the African continent, this doesn't seem like very many, but there are other scholarships available from the Cambridge Trust, from Gates Cambridge, and certain colleges also have further scholarships. A new initiative was launched this year. The MasterCard Foundation has been supporting African scholars for many years, but this year they launched their Cambridge Scholars Programme. And this is the first intake of master's students who were happily waving their MasterCard Foundation flags at the launch event in London in September of 2022. There's also a program, new program, MasterCard Foundation Scholars Programme in Oxford. And the 2 programs have slightly different emphasis. In Cambridge, the emphasis is on climate change, resilience and adaptability. In Oxford, the concentration is on pandemic sciences. So the aims of the MasterCard Foundation Cambridge programme is really to train scholars in a range of different academic disciplines. And these are master's level scholarships. So this is not PhD level, it's to come to study for a master's degree at the University of Cambridge. It's really emphasised here by Pascal Vera, the Pro-Vice Chancellor, that these are awarded to students with a desire and commitment to contribute to climate resilient and sustainable futures for Africa and the world. There's a target of having 70% of the scholars being women, and also to recruit refugees and internally displaced people and people with disabilities. But it's a really great opportunity because there have been 50 scholarships awarded this year for entry into October 2023, and this might ramp up to as many as 100 scholarships for African students at master's level next year and for the following up to 2030. To be eligible for this master's level programme, you must be a citizen of African country, an ordinary resident in an African country. You have to apply for a master's course of up to 1 year in length at the University of Cambridge. And this is across a wide range of disciplines. Chemistry would certainly be included here, but also thinking about this climate and sustainability lens, many different subjects are clearly relevant here. There are taught master's programs and there are masters by research, and both of those are eligible. There'll be new opportunities as part of the relationship with the MasterCard Foundation because there's a research collaborative that's also being formed. This is a photo from the first meeting of the MasterCard Foundation collaborators on the Climate Collective with the MasterCard Foundation Canada, Makerere University in Ghana, Makerere University in Uganda, the University of Ghana, the University of Cape Town in South Africa, and Cambridge universities. Now, these are the founding partners, but we're also planning to have a similar small grant scheme to that presented for the Albarada Awards. And so this will be open to all universities in Africa. So there'll be new opportunities through this research collaborative, although the exact shape of that has not yet been determined. So I've told you about a lot of different things, and there's lots more resources that are available. There's the Cambridge Africa website. We try to keep this interesting and up to date, particularly through our blogs with people who've had Albarada Awards, for example, people who are visiting Cambridge, students, particularly when they graduate, talking about their experiences. The Cambridge Trust is a great resource to look for scholarships. There's also information on the MasterCard Foundation Scholars Programme, and the Gates Cambridge Programme also offers a wide range of scholarships across a wide range of subjects. So I thought there might be some questions about the work of Cambridge Africa. So I wanted to keep my presentation quite brief so there's a chance to answer your questions. But I think I just wanted to highlight the possibilities and show David here in this photo, one of the STAR students. So you can be inspired by your experiences this week and have your eyes open to the opportunities that Cambridge might offer. So thank you. I hope that you're able to still hear me. We'll think of a way that I can take questions from you. Very pleased to take some questions.
So if you have
Hello. So there's a question about, sorry, I'll have to turn this off again. A question about how to find a PI for the Alvarado Research Fund. So sorry for using Cambridge terminology there. PI is a principal investigator. So essentially we'd have an investigator from Cambridge and an investigator from an African university. They spend some time working together to write a short application, which is then evaluated competitively. So how you find the collaborator, I call them PI, but they're interchangeable, is you need to do some research. Who is in Cambridge, who's researching the same area as you? Sometimes there isn't anyone. Cambridge has a very broad expertise, but we don't have expertise in every single subject. So do a bit of research. I mentioned the researchers database we have on the Cambridge Africa website. You can also search online for people in relevant departments. And then you can make contact with your potential collaborator. Cambridge Africa can help you do that. Sometimes it's easier if an email comes from an internal person rather than someone externally. We ask you to write a paragraph about your interests, what you would like to research, why you would like a collaboration with Cambridge, and then we try to do some matchmaking. It doesn't always work, but often this does work. So you need to think of a good hook to interest your potential collaborator in Cambridge. But really, we have this 3-month period, this window of opportunity where you can jointly apply and develop your project. I hope that answers your question. I can see written comments in the chat. Obviously, we're getting a bit of feedback when David was on the phone. But if there are more questions, David, you're welcome to call me back. Does Cambridge University have scholarships for undergraduates? Is a question. We don't have specific scholarship schemes for African undergraduates. Cambridge Trust may have some information about that, but this isn't something that Cambridge Africa is involved with or supports. So some MasterCard Foundation partners, like the University of Edinburgh, have undergraduate scholarships. Cambridge doesn't. We're concentrating for the MasterCard Foundation programme at master's level. So another question about the eligibility status for master's scholarship at Cambridge University. So you need to have a good first degree, at least a 2-1 achieved from your university. You need to show that you are passionate about your research or your topic, and particularly have viewing your topic, your research through a climate lens. And climate and sustainability lens. And this is broadly interpreted. If you were a student of English, you could look at the poetry of climate change. So this is not intended to be very restricted. It's more broad-based. I think for chemistry, there are obvious areas of application that could be relevant for climate resilience and sustainability. So there is more information on eligibility on the website. Essentially, you need a good first degree and an interest in the topic, broad topic of climate change and sustainability. There's also, you need to write a good application. So you need to be accepted by the course or the department, and then you need to be at the top of the list in order to get the scholarship. So if you're thinking of applying, do take care to write strong application, think about how you meet the eligibility criteria, and how you're focused on using your education for the good of the world, essentially. Another question for Alvarado: what's the best way to ensure collaborators respond to emails and accept to collaborate with us? Well, that's a very good question. We can't make anyone, we can't compel anyone to get involved in an Alvarado award. So you really need to be persuasive. You need to think. You need to, as I said, we prefer supporting research that's African led. So if you've got a really good idea, you need to sell your idea, and you need to do that briefly. So let's say you've got an email to do this. You need to say who you are, what you're interested in, and why you want to collaborate with someone in Cambridge. So make that really compelling, short, sharp, and sweet. The other mechanism is to use Cambridge Africa, use the team. It often helps to have an email from introducing a Cambridge email address, introducing you to a potential collaborator, rather than a sort of cold call email from your institutional address. So Paranaz is the Alvarado coordinator, and she can help to facilitate that. So I think they're the two tricks, but unfortunately I haven't got any way of compelling people to collaborate. It's a matter of, well, do your interests align? Is there an interesting project you want to work on together? And is Cambridge a good place to do this? Not seeing more questions in the chat. I'm just checking the comments. Great, we have another question coming up. So I think the question is, do I need to get a supervisor before applying to a fully sponsored, I think that's PhD in chemistry, sponsored PhD in chemistry at Cambridge University? Yes, I mean, I think the steps are that you need to be accepted by the department, which means you have to be accepted by a supervisor. And then you'll go into, once you're accepted, you'll go into the bigger pot to be considered for a scholarship. And so if you, part of it being a strong application to be awarded a scholarship would be having built up a relationship with a potential supervisor, having a good research idea, and being able to present that succinctly in your application form. So yes, now is probably a good time to be thinking of applying, to start looking at who potential supervisors might be, initiating conversations with them, making sure that Cambridge is the right place to do this type of research that you're interested in. It's good for a lot of things. It's not good for absolutely everything. So make sure that you're a good fit. And then I think probably now is a good time to start initiating these conversations, because you have on the application form a quite short small space to really sell yourself and say why you deserve to have a scholarship at the University of Cambridge. Great, so I understand that's the last question. Sorry I couldn't chat back and forth with you, but I understand you could hear me fine. There are contact details as well on the Cambridge Africa website, so please do feel free to get in touch with me or one of the team. I'm sure David can help you with lots of questions as well. Enjoy the rest of your time.
That was beautiful. Write it, write it, write it, write it.
Somebody thousands of pounds to study for free. They want to make sure that when you finish, you're able to use whatever you've learned to make impact in the larger world. Okay, so all of this you need to understand and tailor your application towards whatever it is you apply. So tomorrow is not a mentorship. Then be able to recruit some campus ambassadors. One or two things benefits for us because of because it's not just everybody. You need to make an application for that. And then look at what is driving your passion to be campus ambassador. That will bring you on board. The idea is that on the long run, you will be able to help AODI identify the problems that students are facing, and then we can have a more targeted approach to the kind of things that we bring to you. Okay, so hopefully tomorrow we'll give you more details about that.
Thank you, sir. Thank you. Thank you very much. So tomorrow we'll get to hear more about the mentorship and other programs that we run. So please write down your questions. Write down your questions. We'll be taking them once he returns.
Okay, so before Nick comes, I was only easy. So David actually started with his PhD in Cambridge. I started with a master's. So I want to, so for those of you who are interested in the master's program, forgive me for panting, okay? I just ran upstairs. So I wanted to share with you my experience whilst applying for the Cambridge Master's program from Ghana because I did my undergrad in Ghana. So in 2018, okay, I started applying early because I was a little bit ambitious. So while I was in medical school, I realized medicine wasn't meant for me. So right from 2015, when I was in my second year, I started applying for a master's just to check out how I'm able to get admission. Okay, so at that time I didn't target Cambridge, I was applying elsewhere just to get used to the application process. So after 400, when I got to 400, which is 2016, 2017, I said no, I had to exit. So I was interested in the pharmaceutical and then the biotech industry. So I graduated and then went to work for pharma for about 2 years. Then in 2018, 2019, I started applying for drug discovery courses till I saw MPhil in therapeutic sciences in Cambridge, which was really what I'm passionate about. That is therapeutics and then medical devices and then diagnostics. So at that time, I had gained a lot of experience from several applications. So I made a tailored application onto the program. And then interestingly, my program was very international. So they choose one person from a country, or I'll say continent, because up until now, I've been the only African on the program. So it's very competitive. And then you get interviewed before you actually get admission. And then the interviewing process was also quite interesting. So I would say before you make an application, try and do your research. Some people will enroll on the Aodi mentorship program, don't really do their research. And then during the program, they are now asking, which course should I apply for? What do you mean, which course should I apply for? What is your interest? So before you enroll on the Aodi program, make sure you have an interest in mind, then we can guide you to what you can actually apply for. You get it, but make sure you have a good CV available, have a draft of your personal statement. Also try to practice for interviews, because some of the programs do interviews, others don't also interview. But then luckily I got a £42,000 scholarship for my master's, and then that was how I was able to go to Cambridge. So tomorrow we'll give you more details. I think Nick is here, so I'll hand over to Nick. Thank you very much.
When you are done, maybe take it.
Okay. So thank you for your patience all day, and we hope that the information we provide is useful. Again, all great science is about transferring knowledge. And the promise we made at the beginning, and when we spoke to David and the team quite a few weeks ago about these sessions, is sometimes just bombarding you with information gives you access to the stuff that you may need to use in the future, even if it may not be incredibly obvious what the answer is right now. And it's also just meeting so many people. I only got to half the way through the room, so hopefully this afternoon, tomorrow, I'll get to sort of meet the other half. And also, it's very nice to speak to people and hear Caroline's presentation, because it equips us with the sort of questions for which you will want answers, which we will also pick up tomorrow. I mean, certainly Alex and Bang will tell you a little bit maybe about the computational work they do tomorrow, but I have a little session at the end of tomorrow where, rather than talking about science, we'll just wrap up and explain to you the way we think you should be approaching your careers and the steps you might want to take in deciding what you do next. So to get back to the analytical techniques, there was a sort of very, very fast movement through what we considered to be cutting edge techniques, and then we looked at specifically at NMR. I want to move very quickly through the other techniques now that we routinely use. This is not the sort of very specialized things that someone who may be looking at single molecule recognition will be doing. But what we want to do is to show mass spectrometry, and then IR and UV. There's again two very powerful techniques that supplement what we discussed earlier. Now, what we won't have time to do at the end of the day is a problem session. But what I may do, because we won't want to keep you here too long, is I will show you what I will do later today. I will supplement the presentation and provide it as a PDF, which I hope the organizers will send to all of you. It's high resolution. I know some of the spectra didn't come up very well, especially with the lighting. As long as you remember what I said, when you see the slides on your PDF, which you will have a copy of, you'll be able to say, that's what he meant. Now I see what the multiplet structure is about. By tomorrow afternoon, just make the most of us being here to ask any questions you've got, okay? That's the thing that we want to sort of encourage you to do. We are here as colleagues. We're here as sort of co-collaborators in the great endeavor of sort of doing great chemical science. And now next it's mass spectrometry. Now, mass spectrometry, I explained earlier, is a technique that once it was discovered was used for a while, and then people gave up. They gave up because the technology had not caught up with what people wanted to achieve. And mass spectrometry, let's see if I can get this to work. As a technique, it's relatively expensive. It can be extremely sensitive, which is its utility. Because of the type of techniques, there are now spectrometers which are designed for particular experiments. So if you're interested in protein binding drug molecules and you want to analyze those systems, there are specific machines you have to use and particular type of expertise. Not like NMR. NMR, I explained, we can show someone in about half an hour, 40 minutes how to use, and they can go to any NMR spectrometer in the world and run an experiment. Mass spec is a little bit fussier. It requires a little bit more understanding of the theory. But it works like this. And it's one of the questions that was asked a moment ago about how we get charge in molecules. Imagine you take hexane, a simple molecule like this, straight alkane. Just to be sure, if you ran an NMR spectrum of this, there are 1, 2, 3, 4, 5, 6 carbons, but there are 1, 2, 3 unique carbon environments because the molecule is symmetrical through that position. And playing the same trick we did earlier, we realized that there would be 3 types of proton resonances, even though there are many, many more protons. By NMR, what you do is you take hexane and you really energize it. You put it to such a high energy that eventually it loses an electron from one of its orbitals. Now, hopefully you've done enough molecular orbital theory to know that electrons sit in orbitals. You have the highest occupied molecular orbital, you have the lowest unoccupied molecular orbital. I'll touch on that when I do UV in a moment. If you imagine in hexane that the bond that weakens is this one here, the one that's in red, as you excite the molecule, an electron is removed. According to valence bond theory, a bond is 2 electrons, one from one atom and one from the other, and as they share, they make up a covalent bond, right? Now, if you excite it so much that you remove an electron from that bond, you're left with what is called a radical cation. An unpaired electron, but because you've taken an electron away, that bond is positively charged. This is your excited molecule, and it doesn't like to be excited. It's going to do something to relax. And what it does is it breaks. So the bond literally snaps. And in this particular system, if this bond snaps, there are 2 options. The unpaired electron, the radical, will jump onto this carbon to do this, meaning that the positive charge is on this part here, which is the ethyl cation, or the radical can jump onto this carbon, generating this radical species, leaving the positive charge on that carbon, which is that species there. So far, so good. You excite the bond, you remove an electron, the bond cleaves heteroelliptically 2 different ways. Now, remember what I said earlier on about the mass spectrometer. Anything that's not positively charged vanishes. It gets sucked out by the vacuum pump. And all you're left is the positive bits. And if you've got thousands and thousands or millions of hexanes, if it breaks there, you're going to have lots of these, and you'll have lots of these. And as they move through the spectrometer, what the detector will show is a peak, hopefully at 29, mass to charge units, that's the x-axis, And if we got the theory, the prediction right, you'll generate some of this cation. And the mass of this is 57. Just add the carbon, 12 plus 12 plus 12 plus 12, then the protons plus 3 plus 2 plus 2 plus 2 makes 57. That's what we'd expect. Now remember, all of these systems up until near the end have got +1 charge. They're monocations. And what we are measuring is the mass to charge ratio. But because in most of these examples, the charge is +1, effectively this number is the mass. Now, what does the spectrum look like? Of course, before we look at the spectrum, I very conveniently said that maybe this bond breaks. But because it's an alkane, there's no reason why other bonds can't break. For example, we may decide that the bond that weakens and fragments is this one. And if this is the bond that breaks, you'll get this radical species, which isn't detected, or the methyl cation, which comes at 15, or you get this as the cation, which is 71, and the radical methyl group just gets sucked out of the chamber. Now, when you run the spectrum, if you look at all the combinations, whether you break the bond here, or here, or here, there's no point worrying about this because these are just replications of these. If we break all of these bonds and they're carbon-carbon and they can break equally likely, we'd expect a peak at 86, which is the whole molecule as a cation, at 71 when it breaks here, 57, 43, 29, 15. And when you run the spectrum, that's exactly what you see. So your mass spectrum now has the intensity along the y-axis and the mass to charge ratio at the bottom. For now, let's just say the mass. So what do we see? We see a parent peak at 86, which is the mass of the whole molecule when an electron has been taken out from somewhere. So the whole molecule is flown across as a cation, which is very useful. Sometimes you don't see that. And then you see all the other fragments. You get the 57, you get a 71, you get a 43, you get a 29, you get a 15. Fantastic. It's great when data matches a prediction. It means that it's most probably a hexane. Now, of course, what you'll say when you look at this, you got more peaks. It's not just the ones that you've got all these other things on the side. Some of those you just can't characterize. Because the molecule's so excited, you'll get the natural fragmentations, but sometimes you'll get other fragmentations you can't make sense of. With mass spec, you make sense of the best of the information that's available to you. The other thing, if you take hexane in 5 identical spectrometers in different parts of the world, the mass spectrum will look slightly different because the conditions are different, right? How you injected it, whether the chambers are slightly contaminated. If I run hexane in an NMR spectrometer, in 100 NMR spectrometers around the world, the spectrum will be identical, which is why NMR is also very useful. But that's fine. The mass spec may be slightly different, but they give us diagnostic peaks at the positions that we'd expect. The peak, which is the mass of the whole molecule, positively charged, is typically called the molecular ion or the parent peak. That's its name. And then what you do is you look at all the other peaks and you pick the one that just happens to be the tallest, and you arbitrarily set the height of the tallest peak to 100%. You call that the base peak, and then you reference all the other peaks relative to the base peak. That's the nomenclature, the sort of the jargon of mass spectrometers. So far, so good, right? Take hexane, break all these different bonds. Here are all the predicted. There's a spectrum. Right. Cations, if we think as organic chemists, are not all stable. So if you have a molecule like this where you have a branched alkane, so here's a straight chain alkane, and you have a T-butyl component here, if you're going to break bonds, the bonds that are most likely going to break is this one, this one, this one, or this one. And it's the bonds around that carbon, because if we do the same thing we said before, form a radical cation, making a cation at a tertiary position is more stable. It's stable because of hyperconjugation. So highly substituted carbocations are much, much more stable than secondary, much more than primary. So this is not a straight chain alkane. This is just 1, 2, 3, 4, 5, 6, 7 carbons. But the fragments that we'd expect to see for this molecule is when the whole thing flies as a cation, that's this one, when it breaks here, or here, or here, and that should give us something at 85, or if it breaks here, when that component is a positively charged species, and that's 57. So when we now introduce, chemistry is not just made of carbon or hydrogens. Chemistry is a little more diverse than that, right? And so what about if we add heteroatoms, oxygen, nitrogen, sulfur, phosphorus? How does that change things? Not very much. Same rules apply. Here is a ketone. The key bit is the oxygen, because in that molecule, the highest occupied molecular orbital, the HOMO orbital, is the oxygen lone pair orbital. So if you're going to rip an electron out of that molecule, the place you're more likely going to take it away from are the lone pairs on the oxygen. So if you take a ketone, put it in the machine and energize it, it'll lose an electron from here, which generates a radical cation like this. See, it had a lone pair there. Now it's got an unpaired electron, which makes this positively charged. And this whole thing can fly. You detect this in your mass spectrometer. However, from an organic chemistry perspective, this molecule collapses very quickly into what is called an acylium cation. If you've done organic chemistry, what I do is I take the electron here and I put it down here. And effectively what you do is you take an electron from here and you put it here, and you've turned a double bond into a triple bond, and you've lost this methyl group. That's organic chemistry. If you haven't done much organic chemistry, that may not be, the way we do this may not be familiar, but if you have a carbonyl, you will form a carbon-oxygen triple bond with a positive charge on the oxygen. It has a positive charge. It flies. So in the mass spectrometer, we'd see this as a species. For example, here we have methyl benzoate. There is a phenyl group, the ester, and the methyl. Now, once I take the electron out, the first thing I'll form is this species, which is the whole molecule, but missing the electron. Now the molecule's in a very excited state. And it says, I'm going to do something about that. I will fragment to relax. And the bonds that it will break is either that bond here to form the benzylic acylium cation, which is very stable, or you're going to break it here to give the methyl cation, which is there, or you break it here to form the phenyl cation, which is very, very unstable. You only really generate this in mass spectrometers. You can't do this in a round bottom flask, which looks like this. So take out your calculator. If you take this molecule and excite it in a mass spectrometer and let all the fragments fly and fall on the detector, you would predict that you should see for this molecule something at 136, something at 105, something at 77, and something at 15. And magically, well, not magically, we're good scientists. We know our science. We know our chemistry. You look at the mass spectrum, it looks like this. There's a peak at 136. There's a peak at 105. There's a peak at 77, and there's a peak at 15 down there. So it's fragmented as we expected, and that fragmentation is consistent with having fallen apart from a molecule which looks like this. So mass spec is like thinking person's Lego. What you do is you collect the bits of the puzzle, and then you bring them together to build your molecule. Because, of course, you know what your molecule is, you can do it the other way. You say the fragmentation confirms the structure. You'll see a peak. So the parent ion, the molecular ion, of course, is 136 because this whole thing flies. The base peak, the most stable peak, which we set to 100%, is this acylium system that we've seen before. This is pretty much what you see in ketones and esters. It's the common thing. That is the base peak. Everything else you'll see, one thing you'll notice, you say, there's something at 51. There's nothing here that we predict for 51. What's the 51? Sometimes you can't analyze everything, right? Sometimes there are rogue peaks. But 51, if you've got phenyl groups, is common. 51, if you've got a benzene group on a molecule, tends to be what they call a C4H3 fragment. The benzene gets so excited that it does some sort of intermolecular rearrangement to give a high-energy cation fragment, which is consistent with that peak there. Like the NMR before, this gives us great confidence that we know what we're talking about. Because if we know the chemistry and we do the analysis, if we've made the molecule that we expect, then the mass spec will confirm it. And in these cases, yes, it does. So what you have is you have tables of data, which of course looks invisible here. You'll see it in the PDF, which we'll make available if it hasn't already been sent out. And what these are is common numbers which if you saw them, you got this table on your wall in every mass spectrometry room. You look at the number, and then there are common fragments that make up that number. And those tables are available. You can sort of search for them online. So just like the NMR table that I showed earlier, you get these tables where you say, oh, there's a 15. What is 15 most probably? And you look at, oh, 15 could be a fragment like this. It helps you out. This is where AI is going to help us enormously. We won't have to do this. We'll feed the data into a Google function, and then it's going to spit out the data for you. I don't like that. I like, as a scientist, to look at my data because there may be something which maybe AI has not really predicted. But you, as scientists, should always scrutinize your data. So, are things always +1? And the answer is no. Most times they're +1, but sometimes the molecule you have can be +2 charge. We said in the x-axis that the x-axis is the mass divided by the charge. And if it's +1, it's usually the x-axis is just the mass. If you have metal-based complexes, metals have orbitals from which you can lose electrons to form +2 and +3 systems. Then your mass to charge ratio is the mass divided by 2 or divided by 3. Follow what I mean. Here is a dirhodium, dichloro, octacarbonyl complex. So it's rhodium, rhodium, chlorines between them, and then 4 carbonyls coming off. I'll draw this explicitly in the PDF that I'll show you that later so you can see exactly what it looks like. Now, what do we predict? If it's a direnium complex, 2 rheniums together would look like this. Sorry, a rhenium on its own would look like this. Rhenium plus would be 2 peaks that would be separated by 2 mass units, and they'd be in the ratio of 37 to 63. And you think, oh, that's very particular. Why is that? Because rhenium has 2 naturally abundant isotopes that are separated by 2 mass units, and it's rhenium-187, which is almost twice as abundant as rhenium-185. So if you've got a direnium complex, a single rhenium would look like this. If 2 rheniums fly in your spectrometer, you'd expect a pattern like this. That's the peak that results from 2 rhenium-185s. This is the peak from 1 rhenium-185 and 1 rhenium-187. And this is the peak for 2 rheniums-187. And knowing the intensities, you work out they'd be in the ratio of 14% to 47 to 39. And now we keep playing that game. You say, well, if we're right, if we've got 2 rheniums and a chlorine, you'll get this pattern because chlorine exists in 2 isotopes as well. And if you've got direnium dichloride as a cation, you get a pattern that looks like this, separated by 2 units because they're separated by 2 mass units here. And the intensities can be worked out. And why are we doing this? Because if we look at the mass spectrum, look at what we see. An incredibly complex spectrum, but beautiful in its simplicity and in the information it offers. If you look at up at around 650 mass units, you get a pattern which is representative of 2 rheniums, 2 chlorines, and 8 carbonyls. That means the whole molecule as a +1 charge. That's fine. The carbon monoxides fall off very easily. So what you see at the equivalent of 12 plus 16, 1 carbon monoxide unit below, you see exactly the same pattern repeated again. That's when it's 7 carbon monoxide. If you lose another carbon monoxide, you have 6 carbon monoxide. The pattern looks the same. The intensity changes because of how stable it is, but you lose another carbon monoxide, another carbon monoxide, another carbon monoxide, another one. At this point, it's rhenium-2, chlorine-2, 1 carbon monoxide. Now you lose the final carbon monoxide and you get the pattern that we saw before. These patterns can be easily predicted, and here they are. That is definitive, right? That is science. That is, if someone says, yeah, do you really think you've made this compound? Oh yeah, we've made this compound. And this mass spec tells us that we have, and that the things that break apart easier are the carbon monoxide before the rest of it falls apart. However, there's something interesting. This is up at around 400, 500, 600 mass units. If you divide all of these by 2 at half the molecular weight, you see each of these patterns replicated half the molecular weight. And you say, well, that's fine, because all of these are these when it's 2 plus charge. In other words, when you've removed 2 electrons. So by seeing the same pattern, but at half the number, it is even more unequivocal proof that we have the rheniums in the system, which can lose 2 unpaired electrons. Now that, by the way, from a metal and an organic perspective, is a hard spectrum. There's a lot of data there. But the point is, it's the same pattern, just replicated over and over again. Straightforward. So mass spec is really, really powerful. And these are the examples around which we would base a whole sort of multi-lecture mass spec course, because it gives us the basic knowledge, the basic tools to understand mass spectrometry. Now remember, most other things we call NMR spectroscopy, ultraviolet IR spectroscopy. This is called spectrometry because literally we are measuring, metry in Greek, we are measuring masses. But the other things, we are seeing spectra, we are seeing phenomena. And you can do very cool stuff now, of course. I mean, this is one of the experiments that colleagues in the department have done, where what they're taking is they're taking complexes of proteins that are held together with little organic molecules, drug molecules, and they're able to run the mass spectrum of these complicated assemblies by mass spectrometry, but not by shattering the molecule, not by fragmenting it, by letting the complexes coming together tickle electrons rather than smashing these molecules apart. You just knock electrons off, and these compounds are so big and they've got so many unpaired electrons that what they're detecting is something with a charge of 25 plus, 26 plus, 27 plus, 28 plus, 29 plus, and so on. Now, this is a whole field that could make up a whole different course. The message here is that the fragmentation is useful as a tool for what mass spec can do, but there are much more sophisticated techniques that we do that are based around sort of chemical biology. Okay, so now keep again eye on time so that we can sort of wrap up, because you've been in here all day, and also to give us an opportunity to chat. The last thing we'll do is to quickly power through UV, visible, and IR. These are the ones, I think, techniques that are much more familiar to you all. They are because they've been around longer, they didn't do anything exciting the molecule. You're essentially promoting electrons or stretching bonds. So let's look very quickly at how this works. You should be more familiar with this. I just want to show you a couple of interesting examples. So UV visible spectroscopy is relatively cheap, pretty easy, right? You just put your sample, press a button, and you get your spectrum out the end. It's robust. What you're looking here is at the absorption of light by your molecule. So you put light into the molecule, something gets excited, usually electrons between orbitals, and you see what wavelength is absorbed. So here the spectrum has got, I mean, again, you can't see it, but it has different absorptions. So if it absorbs here, it's sort of red, it goes down all the way, blue, violet, and so on. So the different absorptions you'll see in the PDF shows you how just giving absorptions only a few wave numbers apart is diagnostic of the molecule in different ways. Now remember here, the important thing here is we need to have a chromophore. A molecule from a practical perspective that absorbs is one that has an energy gap, and this is something I think Alex and Bang will talk about tomorrow in terms of molecular orbitals and how you can compute and predict UV spectra. That in the simplest sense, UV spectroscopy says, if you've got a HOMO-LUMO gap, you absorb light and you push an electron from one orbital to a higher orbital. And as this gap, once you get the wavelength right, so that E equals h nu, wavelength or frequency, when you get it right, it absorbs. It'll only absorb at the right wavelength or frequency to jump that gap. That's what UV spectroscopy is about. Now that gap is a particular value, but that gap can be either small or it can be big. Depends on your molecule. Okay? Different gap size, different absorption, different UV visible spectrometry. I mean, of course, UV visible, the question is, does it absorb in the visible or does it go into the infrared region? Or, sorry, the ultraviolet region. For most organic molecules that we're interested in, the absorptions that you're interested in from one energy level to the other, the HOMO to the LUMO, is usually a pi to pi star transition. In basic language, you need double bonds. Double bonds are very good for this type of spectroscopy because they absorb in that region. So that's what the picture would look like. If we draw a very simple molecular orbital diagram, we say that for a simple alkene, that's carbon double bonded to a carbon, the p orbitals overlap to give a pi and a pi star orbital. And what we're interested in is that HOMO to LUMO gap from here to here. So if you have one alkene, that gap is whatever it is, and it absorbs at a particular wavelength. What happens if you have two alkenes next to each other? If we draw the molecular orbital diagram for butadiene next to ethylene, that's two double bonds separated by a single bond, means they can communicate to each other. The molecular orbital diagram looks like this, a little more complicated. The key point here is that the HOMO-LUMO gap is smaller than the HOMO-LUMO gap here. If the gap is different just by having one double bond or two double bonds next to each other, if they communicate, this must be a very, very sensitive technique, and it is. Look at these two molecules. Lots and lots of double bonds. Double bonds can conjugate. In other words, the electrons can delocalize. Double bond to double bond to double bond. As long as they're separated by a single bond, they communicate to each other. Take those two molecules and we count how many double bonds are next to another double bond. And if we count them in the red box, both molecules have 11 double bonds. At this point, you're thinking, well, they'll give identical spectra, right? If this is about pi to pi star transitions, 11 bonds here and 11 bonds here are going to behave exactly the same way. And that's exactly what you predict. What you notice, however, that's not what happens. The top molecule doesn't have 11 double bonds that talk to each other. It has 9 double bonds that talk to each other. Because the double bonds at the end, that one and that one, cannot sit in the same plane as that molecule. Sterics tip those out of the plane. So the bottom one has 11, the top one has 9. At this point, you may say, well, what's a couple of double bonds amongst the 11? And the answer is the following. The top molecule is keratin. It's what gives orange carrots their color orange. The one with 11 double bonds at the bottom is called lipocene, and it's what gives tomatoes their red color. So that double bonds at the end make a significant difference. And that's the classic example of explaining how delocalization affects the pi-pi star gap, and just by changing the number of double bonds does affect the appearance of the spectrum. Now, remember, carrots traditionally are not orange. They were traditionally white and sort of browny color. It became fashionable in Europe to get orange carrots when the Dutch sort of engineered orange because it was the royal color, and orange color carrots are orange everywhere now because of a royal fad. As chemists, what we're interested in is not about history. What we're interested in is that one species of carrot has evolved biochemically a molecule that looks like this, and those 9 double bonds are what give its characteristic color. I'm sorry to ruin your dinner next time you have carrots and tomatoes, and you're not going to think about flavor, but you're going to think about molecules. But their simple difference is 2 double bonds. Now, if conjugation matters, here is another conjugated system. If we think a bit more chemistry, it's a phenyl group. We've seen this molecule before. It's a phenyl group next to a carboxylic acid. The double bonds can delocalize and conjugate with the oxygen-carbon double bond, and therefore you get absorption in this position. If we put an extra double bond between these two groups, so you have a greater delocalization pathway, the absorption goes to higher wave numbers and it becomes more intense. They're the two properties. If we now say, okay, let's look at this systematically. Here is a system. We've got 2 double bonds next to each other, 3, 4, 5, and so on. Every time we add a double bond, the wave numbers go to higher numbers and they become more intense. They absorb higher. So this is the spectra on top of each other, and you can see with each one it's pretty much the same pattern, but it's moving more to higher wave numbers and they're becoming more intense. So if I look at this and say if there's 2 of these, it absorbs at 227 nanometers, And epsilon is what is called the extinction coefficient. It's a measure based on an equation of how much it absorbs. As we move to more and more double bonds, we get to higher and higher wave numbers, but look at what happens to the extinction coefficient. It goes up by an order of magnitude because of this delocalization, because the pi star gap is getting smaller and smaller. So that's combining your theory with the UV spectroscopy and looking at trends to understand the whole system. But it doesn't happen just with carbon-based systems. Those of you who say, yeah, sure, but cobalt complexes are not made up of carbon. Why metal-based complexes? Still, it's a HOMO to LUMO transition, but now it's not a pi to pi star transition. Metal-based systems, if you make a metal complex, takes the 5 degenerate d orbitals, and if you turn off the octahedral geometry, they split according to this arrangement. So if you have something like a copper D9, the electrons look like this. So if you absorb, the HOMO-LUMO gap is between here. So metal complexes absorb because of the HOMO-LUMO gap in the transition d orbitals, not in the pi star. Right? Just orbitals at the end of the day. We just give them different labels. So that's UV visible spectroscopy, something that you know very, very well. And the last thing, and we'll be done just under time, maybe gives a chance to maybe just even ask some questions, is IR. And again, IR is a very good technique because it's cheap, it's pretty robust, it's accessible. But what this measures is the energy that's required for bonds to vibrate. We're not looking at energy electron transitions. We are literally just looking at the energy in the IR region. It's heat. Remember, IR is heat. IR is a component of sunlight which heats us. We're essentially heating bonds and making them vibrate. If I had a simple molecule like this, the best representation is like having 2 balls and a spring. IR measures how much energy it takes for the spring to vibrate. And what affects the spring vibrating? How stiff the spring is, in other words, how strong the bond is, and how big the balls are on either side. A key thing about IR is that the more symmetrical the bond is, the weaker the absorption. You want the bonds to be unsymmetrical. In the language of physical chemists, you need to establish a dipole. Because when you apply IR, what's shifting is the dipole in the bond. So the better representation is a bond like this, where you've got a smaller sphere and a bigger sphere. Now you've got a dipole, and when you do IR, you watch how that bond vibrates. Let's take a carbon-carbon bond. It's symmetrical. We won't worry about that. It's a single bond. Shouldn't be too easy to vibrate. If you go to a double bond, well, that's a stronger bond. It's a shorter, stronger bond because you have a sigma component and a pi component. It should take more energy to vibrate. If we go to a triple bond, a CC triple bond, well, that should be harder to vibrate. And if we play the last trick in the book and now say, well, why don't we put a carbon and another atom, so we have a greater dipole, something, for example, like carbon-oxygen double bond. If we compare the stretching frequencies here, they look like this. A carbon-carbon double bond absorbs at around 1650 inverse centimeters. A carbon-oxygen double bond, remember, they're both double bonds. But by making this a heterodiatomic, the 2 sides are different, we have a bigger dipole, so it absorbs at a higher number. It's also going to absorb more strongly. You get very strong, intense peaks. And then finally, we have cyanide, CN triple bond, the cyano functional group. That's a triple bond, and it's got 2 different atoms, so it's got a dipole, and that absorbs all the way up at 2250. So numbers tell you about the functional groups. That's what IR is about. So when bonds vibrate, it's not just like the spheres on a spring that vibrate like this. Sometimes functional groups have got bent components. So if you look at SO2 or NO2, that functional group is bent. It's like a sort of V shape. And theoretically, the way it's going to vibrate is 3 ways. A single bond vibrates backwards and forwards, backwards and forwards. A bent functional group like this will either bend asymmetrically. This looks a bit silly when I do this, but it's going to do this. One's going one direction and the other follows, or it's going to do this symmetrically. This hurts. They're both moving in the same way, opposites. Symmetrical and anti-symmetrical. But when it's bent, it can also do this. So theoretically, there are 3 ways that a bent functional group can stretch. And if we look at them, that stretches at 1360, that at 1150, and that at 1540. And if you run the gas phase spectrum of SO2, which you'll see better in the PDF, there's an absorption here at 1400, there's one here at around 1150, and there's a tiny one here at about 1540. That's great, because that proves the principle. We now have a marker by which we compare these functional groups when they appear in other molecules. And likewise, if you take carbon monoxide as a gas, it's a triatomic system, but it's not bent like SO2 or NO2. It's OCO in a linear fashion. The one absorption this lacks is the bent one, the one that goes like this. The molecule's linear. So the way it's going to stretch is either like that, or in a way that's a little bit more difficult to do. The 2 ends, sort of, my fists and my head move slightly different. A bit like a bird flying. If we run the IR spectrum in the gas phase of CO2, not surprisingly, we see 2 peaks. One at 2360, which is nice and intense, and a weaker bending one at 670. Proves the principle. We understand the fragments, which means you can go and look at sort of more complicated spectra and see what information we get. And just like the other techniques, there are tables of data which say from about 3,000 inverse centimeters down to about 1,000. Up here you have OH stretches, and you got NH stretches, and you got CH stretches, and CN triple bonds, CC double bonds, and so on. So depending on where your stretch appears, it gives you a rough idea of what functional group you have in your molecule. So run your IR spectrum, look at where the key peaks are, go and look up a table like this and say, I think I know what functional groups I should be looking for in my molecule. So here's a couple of examples to look through quickly. Ketone, sort of molecule we've seen before. If we look at this, what would we expect to see? Well, this molecule is made up of a lot of CH bonds, right? If you look at this, it's an alkane at part. CH bonds, CH, 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 CH. And up at around 3,000, you always see absorptions which are representative of different type of CH bonds. They're always there. Not surprising. The one that really matters is the peak right here at about 1715. It's a big, intense, sharp peak. That at 1750 is a carbonyl. It's a Ca double bond. And that's what we have in the molecule. That's exactly what we see. Now we're going to see lots of other peaks around here because we've got CC and CC. They're not important for us. They're just noise that comes with the molecule. What about, and so these are all the other bonds that I've got in blue. They're there. We're not going to spend much time analyzing them because they don't tell us much about the molecule. Look at this molecule now. We've changed the carbon-oxygen double bond for a carbon-nitrogen triple bond. What do we see here? Well, we see all these CH stretches at about 3,000. And then at 2250, we see a super sharp, intense peak, which is in exactly the right region for a CM triple bond. Your molecule has that functionality. And of course, you have all the other bonds, the absorption, which are there, but we're not going to spend much time thinking about. Take this alkene. It's a terminal alkene. What do we see here? Not surprisingly, we see lots of CH stretches at about 3,000. We said we should always expect them. They're there. You get lots of these CC bonds that appear throughout, not very useful. But you get a peak at about 1650, which is sharp, relatively intense, and that's diagnostic for a carbon-carbon double bond in an unsymmetrical molecule. So we're just using the tools. We're using that table that we saw a moment ago to just extract data from a table. Again, this is the sort of thing that we're told that machine learning and AI will do for us. You'll just feed your spectrum straight from the computer into a program. You won't even look at it now. It's going to see what peaks are there, and it's going to tell you what functional groups it's got. But this is how it's going to do it. Okay, I think the last two techniques, talking to many of you today, are those that are more familiar to you. But I thought it'd be very useful to give them with a set of examples that consolidate the concept. And with all presentations like this, my view has always been that if at the end of a session you walk out the door and you think, I've learned a lot of stuff I didn't know, that's really useful. And if you've walked out of the session today and said, you didn't really teach me anything new at all, that's great because it confirms that the basics that you need to know about the technique, you do know quite well. So either way, it's a win-win for you, okay? Now, what I was going to do, which we won't do because you're tired and you've got better things to do, and I will deal with afterwards, is what I was going to do is work through a couple of problems that look like this. I got these from this book, Organic Structures and Spectra. This was done by my PhD supervisor back in Sydney. It's a book which goes through these concepts and then has pages and pages of problems for you to work through. And I've extracted some examples. And what I was going to do is we're going to work through these together, but I've done a couple just to show you the way you should approach this. And what you have is you have the IR spectrum, the UV spectrum, the mass spectrum, the carbon and depth, and then the proton spectrum below. And this is ethyl iodide. It's a molecule we've discussed already. And what you'll see here is that it has no interesting stretches in the IR spectrum because there are no interesting functional groups. So not surprisingly, nothing exciting. The UV spectrum has no intense absorption in the exciting region other than it sort of absorbs a little bit because it's got the CI bond, which absorbs a bit. But the mass spec has peaks that tell you the molecule is breaking here or here. And the peaks appear in the mass spectrum in exactly the right position. By carbon NMR, we see two carbon peaks, one at a higher chemical shift than the other. One is a CH2, one is a CH3, so in the depth they appear in opposite directions. And in the proton spectrum, we see this as a quartet and we see this as a triplet. They're right there. So what I want you to do if you're interested in your own time is work through the problems, and I will have the structures, and I'll put a couple of key hints here, the key elements of the structures. And for example, for the next one, it's a ketone, and what you have is an IR stretching frequency, which is diagnostic for a carbon-oxygen double bond, mass spec peaks, which fragment there and there to form the acylian cation, which we've already encountered. We have 1, 2, 3, 4 carbon peaks with a diagnostic carbonyl carbon up at about 200 ppm. And in the proton spectrum, we have a methyl singlet because the 3 protons couple to nothing. There is a quartet, there's a triplet, and so on. And there are some examples. Here's a nitro group, here's a carboxylic acid, and everything should be exactly as you'd expect. Here, for example, you'd see absorptions for the CHs, the carbon-oxygen double bond, the OH. So these all come at exactly the regions you expect. It fragments here, here, and here. 1, 2, 3 carbons, 1, 2, 3 carbons, 1, 2, 3 protons, 1, 2, 3 protons, and the rest you can do. This, I hope, is fun. This is the sort of thing, put on some music in the background, make a cup of tea, take out a chocolate bar, and just work through the problems. All they will do is they will confirm how you apply these techniques in a constructive way. We hope that this has been a useful session. I will, if the material has not been made available online, because I know that it's come up terribly bad on the slide, I will add my bits at the end in the next hour or so and then make a PDF, and I'll get the organizers to send it to all of you, and please look through it, and hopefully you'll be able to make a connection between what I said and the notes that you made and the better slides. That's about it. We were going to go till I think 4:30 or 5, but I think you've had enough. Maybe if there are any questions for a little bit of time, if you've got any questions about the techniques or anything we've discussed so far, happily try and answer them. And when we're done, it's better maybe to go outside and chat and meet and sort of interact a little bit more. So you have a question? Someone put their hand. Anyone have a question? That was answered.
Please put your hands together for Dr. Link again. All right, do we have questions? Do we have questions? Do we have questions? Okay, please come. Could you please hurry up, sir? Thank you. Some of us are stretching. It has been a day. They came before us, and they are not stretching. And we want to rule the world.
Good evening, sir. I thank you for the wonderful presentation. My name is Nadi Samuel. My questions are, you are mentioning the instruments. So my question, and you are saying that most of them are expensive. So I'm just wondering, is there a way we can assemble the parts over here in Africa and reduce the cost of those, both the UV spectroscopy? Like, can Africa start producing scientific instruments that can also be used in scientific research? And the next question is that on the slide, I was seeing carbon 13, that is the mass number of carbon 13. So I'm asking, what's the significance of carbon 13? Because normally we know carbon 12. Thank you, sir.
All right, for your first question, I think that should go to the HOD, the Dean, when Africa will produce that. It's not for our guests to answer, but your second question, I think he can do that.
No, I mean, in terms of techniques, they are expensive. IR and UV is much more accessible. You can buy a lot of packs that you literally carry in a bag anymore. I will talk to David and the team. If there's any way we can help, we will. Some things like NMR and mass spec are more complicated because the ongoing running costs. I'm talking about someone who's worried about how we pay for this back in Cambridge. An NMR spectrometer may cost, a good one, 150,000 pounds, which is a lot of money. But they cost about 10,000 pounds a year to run. Liquid helium, liquid nitrogen, electronics, maintenance costs, etc. You can't really put together mass spectrometers anymore. They're just too complicated. Sometimes you can jerry-rig and come up with some UV and IR. But what I hope we can do is collaborate in a way which we can encourage universities to exchange equipment, or just so that we need to think. I'll speak to David and the team. The thing about carbon-13 was a very, very clever question. And I jumped over that completely. Of course, the most abundant isotope of carbon is carbon-12. But carbon-12 is not spin active. By NMR, it just gives no signal. So you rely on the one isotope of carbon, which is spin active, which is carbon-13. That's why we see it. The downside of that is carbon-13 is only 1% abundant. 99% is carbon-12, which is why we said carbon-13 takes longer to run, because there's less of it. So there is a fundamental reason why we don't run carbon-12, but you run carbon-13. Hydrogen, in its most natural state, H1, is 100% hydrogen. So it's perfect. Not only do you detect it very easily, but if you have a hydrogen next to a hydrogen, they see each other and they talk. I never talked about carbon-carbon coupling, because carbon-carbon coupling is really difficult. Because carbon-carbon coupling in a carbon-13 spectrum requires a carbon-13 to be next to a carbon-13. But the chance of that happening is 1%, because carbon-13 is only 1% abundant. So your question is a very wise and insightful question, that not all the nuclei that we acquire by NMR are the highly abundant ones, which is why we don't worry about carbon-12. The same with tritium, there's different isotopes of things. It's isotope abundance. Good question. I hope that answers the question.
Thank you, Dr. Nick. My name is Evaristus. My question is with respect to IR, especially the vibrations of molecules with the carbon dioxide. My question is, now that we are talking about climate change, can we actually identify the particular vibration of the carbon dioxide that is responsible for GHG? Sorry.
there's a whole field of atmospheric chemistry, and we have we have 3 large groups in Cambridge that just work in atmospheric chemistry. So carbon monoxide is carbon monoxide. It is what it is, and there's nothing else about it. But in the atmosphere, reactions happen high up that don't happen at atmospheric level. Because they're irradiated by UV light high up, you get fragmentations and changes which may give slightly different spectra, so you can characterize them. But that's hard. And the way they do this is the following. One of my colleagues, I can't say he did this, but got funding to buy an aeroplane. Not something you go and shop for regularly. And what they did with a big European grant is they took a small aeroplane and they stuffed it full of mass spectrometers, and IR spectrometers and HPLC, etc. And they'd go to different elevations in the atmosphere, and they would fly around for a while, and then they would just measure everything in the atmosphere they could. And they go higher up, and they measure everything in the atmosphere. They'd go over London, they'd go over Cairo, they'd go over Rome, and they would do exactly the same thing again. And what they detected is a profile of all the reactive species in different altitudes and in different countries. So they tried to make a 3-dimensional map of the sort of chemistry that was happening in the atmosphere. So that work is done, and it can be analyzed using these techniques. But remember, with molecules like carbon monoxide, it's on its own, it's a single molecule, and it can only do this. You need them to be part of some other system to make it see something more interesting. For example, if carbon monoxide in the atmosphere has an electron removed or has got some functionalization, it will change it, and you will measure it by IR. But at atmospheric, I mean, here, it's all pretty standard. But higher up in the atmosphere, yeah, they're doing this. What they're trying to do, of course, now they're trying to do it from space. They're putting satellites up, and they're sending lasers down and detectors, and they're looking at, you're basically doing spectroscopy in reverse. And for a while, something we stopped doing, there used to be a green laser that used to come out of the top of the chemistry department and shoot into the sky. You could see it miles away. And I thought, what is this green laser that's poking out the top of the building? And basically, our atmospheric chemists used it. And what they did is they shone a laser at a particular wavelength or whatever the detail was, and they could measure the backscattering of molecules in the laser path and characterize what was happening above the department at different times of the day and different times of the year. And they're doing this with laser in reverse. They've got very sophisticated equipment that they take over the oceans, they take over the ice caps, and they just IR and UV, and they look at backscattering, and they have base stations, and they look at what comes through. Fantastic science, but incredibly complicated. But when you're working with small molecules, your choice is somewhat limited. That's why we're more interested with organic molecules that are bigger, more complex, a lot of C bonds, CH bonds, and so on. For the practical organic, inorganic, synthetic, medicinal chemistry, it's complicated systems like that that we're more interested in looking at. Your question is a whole field of research, so go for it and good luck.
Please, let's make you quick. Introduce yourself.
My name is Evans Ugoke. I'll go straight to my question. You talked when you did this mass spectroscopy, before fragmentation, you excite the molecule, and you made mention about introducing a positive and negative center. Then my question is that how do we introduce that positive and negative center before that fragmentation? I mean, I couldn't get it.
There is no negative center. There is no negative center. There is no negative. When you excite it and you rip an electron out, the only thing you form is a positive thing. So that's the important thing. So when you take your atom and you knock out an electron, it's always positive. There's nothing negative ever. So you form a radical cation always. So if I'm a molecule and I've got a pair of electrons on my ear, like a carbonyl, if I knock an electron out, the electron just disappears. All that's left is a cation. It's always a cation. And it's the cation that then breaks into a radical and a plus bit, and it's the plus bit that you measure. That's all it does. So if you take a molecule in the lab, it's neutral, completely neutral. Put in an ionizer, Excited, if you're excited enough, you take an electron out, you're left with a positive radical. It breaks into a radical and a cation. The radical gets sucked out because it's not going anywhere. The positive feels a positive charge on one side and it Yep. I can show you later, yeah, in more detail.
Good day, everyone. I have two questions to ask. Okay, my name is Izugu Chimizi Fabian from 300 level pure industrial chemistry. My question goes like this. In the morning, you said something about clusters of protein in the brain, forming kind of sponge or something like that. And you said that to analyze that protein molecule, we are going to make use of a kind of spectroscopy known as electron microscopy, something like that. And since you said that kind of spectroscopy is a very, very expensive one, can we use other form of spectroscopy, like the UVIR, to analyze that protein that is responsible for the Alzheimer's disease? Then the second question is, just like carbon 13 is a specific isotope used for getting the signal of NMR, carbon to carbon listing. Can we also use, is there a specific isotope for hydrogen that you can use to analyze NMR signal for protons? Thank you very much.
Yeah, very quick answer. In the stuff where they're looking at Alzheimer's, it's really electron microscopy that does this. Because what you're looking at, you're trying to look at how proteins aggregate to form little clusters. And you're doing this with a microscope. You can't analyze them by NMR because they're insoluble. That's their problem. When these microfibrils form in your brain, they become hard, they don't dissolve. Because you can't dissolve it, you can't run an NMR of it. So we're stuck. So it has to be electron microscopy. You can functionalize them with fluorescent proteins so you can see them under an optical microscope as well, but they are very, very small. So you need very specialized techniques. You can't do this by the techniques I just mentioned. You can't ionize them, you can't dissolve them. That's a problem. And maybe one could argue that's why for a long time people didn't know how to characterize them, because they didn't have the right tools, right? But now the more people are able to see them, literally see them, now they're starting to understand them. And your second question on isotopes, for hydrogen, the one isotope is hydrogen 1. You can have deuterium and tritium, they're the other isotopes of hydrogen, and they're all NMR active. But hydrogen 1, proton, is 99.9% abundant. And it's very useful, which is why we use it. It's always there, we see it, and one will couple to another one next to it. Deuterium, a question that was asked earlier on, what solvent would you dissolve your compound in to do NMR? In a solvent that doesn't have hydrogen. So typically you use CdCl3, deuterated chloroform. Why? If you use protonated chloroform, CHCl3, in your NMR, what you're going to run is a spectrum of the chloroform. Because your chloroform is in huge excess compared to your compound. So use deuterium, it's the same, but it's invisible to the proton NMR spectrum. You can change your spectrometer to acquire deuterium, in which case you see deuterium and not protons. You can do tritium. Tritium is actually a good nucleus. Proton, it's effectively nuclear, right? It generates radiation. We can't use tritium in a normal lab because if it escapes, it gets into the system and it causes terrible cancer. So the three isotopes of proton all are NMR active, but proton is the one that's the most abundant and the easiest one to use. Sometimes, again, not to extend the thing, if you take a molecule and you want to change a part of it to see what happens, you can change one hydrogen for a deuterium and run the spectrum, and they behave exactly the same way, but you run the deuterium and the hydrogen spectrum. I can show you in a separate example, and you get specific information. But all of hydrogen are spin active, but proton H1 is the most abundant and the easiest one to analyze. Colleagues have tried to do some solid state NMR on this, some stuff for Alzheimer's, since they're solid and they don't dissolve. That's hard, but people are trying to do with solid state NMR, where it never dissolves, but that's a whole different field, and that's something for another time.
Thank you, Dr. Nick. One last question. Where is he? Dr. David. Dr. David Izogo. Are you close by?
Okay, Nick, thank you so much. I still have one question for you, Nick. I have one question for you. Okay. Yeah, so I've been receiving lots of questions around. One of the key things we wanted to do today is the hands-on part of whatever spectra you're trying to analyze. And I was having a conversation with Nick, and I told him why this is very, very crucial, why I feel it was very, very important that we do this. During my master program in Japan, I had access to all the facilities you can think about. So there were some students I was helping to analyze some compounds. So they run their synthesis here in UNN, and then they send it all the way to Japan. Now there were about 5 of them, which means I needed to, outside my own masters, do characterization and analysis and all of that for 5 sets of students with all of the organic compound they've synthesized, then the metal complexes that come with it. And each of those compound organic molecules usually have like 4 or 5 metal complexes. So you're talking about maybe up to 15 samples per student. So that's an enormous amount of sample to help someone to analyze. But life would have been better for me or easier if those students had the software to extract the raw material, the raw data, so that I just go to the machine, acquire the data, and then send the raw data to them. And they're able to use, I don't know if you listened during my speech, there was a place I said, why will it take me 3 months to synthesize a compound, 6 months to send it out, only for the results to come back in a plain static sheet with all the information lost? There are so many things. If I have a raw NMR data and I have like top spin, I'm able to use that to extract a whole lot of things from that result. What kind of communication one NMR is having with another, the splitting patterns, a whole lot of things. But if I send you a static printout of one sheet in a PowerPoint or something else, the entire characterization you've done for that compound is lost. So part of the things we wanted to achieve today was to have an opportunity to use some of those software, get a raw data, and then see how you do the swimming and everything, and then be able to read your spectra and all of that. But unfortunately, since yesterday, even while we landed in Lagos and trying to find our way here, we're trying to look for the adapter to connect to Nick's laptop, but we couldn't find that. We came here, Solomon went out, running around trying to see if we can get that. And the software in question is already installed there. So there's no way for us to connect to that. That's the reason that simulation did not happen today. But knowing the importance of that, this now comes to my question, Nick. Is there a way we can make up this? Is there a video we can get online that is going to teach people this? Or are you happy maybe when you're back at Cambridge to do a video recorded thing, you know? Because sometimes the way I understand things that somebody's telling me is probably directly proportional to if I know who is talking. They've related and interacted with you. I know they're going to better even understand what you're saying in a video than just going to YouTube to just pick that up. So if we're able to get that, then we're already in the email. For those of you who registered, if you didn't register, I think the registration link is still open. Just register and select whether in person or virtual, don't select in person, so that we have your email and we're able to send you materials. Okay, because that's the only way we can access it. We don't have anybody's contact or that. So you should go back. If you registered before because you realized people made mistake in their email, and you didn't get any of our email, go back to that registration site, register again so we can have your email. So if there's any communication we need to make, we'll make with you. So Nick, I don't know where, we've sent the link to download the top spin. It's free. Okay, so once you use your university email, recognize these institutions, it's usually free. So I don't know, I think the other session, because this is something most of you might not have been opportunity to see or use. So I still believe that you need, rather than just getting the software, installing it and playing around, if someone should speak to you about the easiest way to manipulate things, it will be easier. And maybe alongside, maybe Nick can also send some couple of raw data for a couple of NMR samples that have been acquired. I think the NMR one is the key one. The UV and IR, people can usually use even Excel to simulate, to bring out and analyze the spectra. So Nick, I don't know what you think.
I mean, very, very briefly, UV and all the other IR mass spec, they're very easy. There's nothing to manipulate. I mean, they're just literally lines. But I accept the point about NMR. There is great value in manipulating the software. Time and technology just didn't make that possible today. When we train people in Cambridge, it takes less time to train them to run a spectrum than to train them to process a spectrum carefully. Because NMR, just to run it, to put it in, spin it, lock it, and acquire is routine. But to do processing takes more time, and very often people learn from others. So what I'll do is we'll find the best way to do this, even if it means I sit down and I do a bespoke, having met and spoken to you now, I can do a bespoke presentation that you can watch whenever you want. And if need be, we can have a session, because we're the same time frame, where I can do something online to sort of go through and do it on the screen and talk through. We'll find a way to do this. And there's something that David mentioned, was a PhD student in Cambridge. I remember he made the point then. Yes, we'll find a way to do this. Certainly for NMR, it is a much more useful tool. I was surprised that you could actually download the software free. That's incredible, because Brooker, who is the largest supplier of NMR spectrometers, they make the world's NMR spectrometers, would charge a fortune for a license. Finally, they have an enlightened view, and to academic users, they're making it free. If you download TopSpin, there's raw data on there as a teaching aid. So what I was going to use is cyclosporin and cholesterol. They have 1D, carbon, depth, APT, COSY, NOSY, headquarters, they're all there. And that's the sort of thing I was just going to put on the screen and point and show you the key features. But David, let's talk offline. I think the priority for me, if you agree, is I'll go away and add information to the problems at the end, so you can work on your own, so you can now use information. I'll send it to you as a PDF, and then we'll find a way in which we can get something that you can see in your own time or do interactively. David, I hope that's okay.
Okay, thank you so much, Nick. I think because we skipped that, it simply means we are ending the session for today earlier than intended. So I think So ahead of tomorrow, we lost quite a lot of time today trying to get the technical things to work and all of that. Tomorrow, we've spoken to the people in that room about opening up this place, so they're happy to open it up at 8. Hopefully 8:39 we can get started with things, because there are quite a lot that we need to do tomorrow. Nick has been saying a whole lot about the experimental aspects of all of this characterization, but there was something. Maybe I'll tell you a little bit about my PhD, in case some of you that weren't here when Nick mentioned that. Alex Stone was actually my PhD supervisor in Cambridge. So I usually tell people he's the world best supervisor. I'm always lucky when it comes to getting supervisors for academic endeavors. My master's supervisor in Japan was also amazing, and all of that. And I think one thing about supervision is, providing the enabling environment for you to be yourself, explore your environment and all of that. While I was at Cambridge, apart from the academic aspect of things, I was fully involved in student leadership, your SCG and all of that, at the school level, faculty levels, department level,
college and all of that. And he provided the support that, allowed me to combine my studies and all of those activities. And one thing, when people ask me, what is the highlight of your being in Cambridge? They usually think, expecting to say, oh, amazing research, academic excellence, and all of that. But guess what? Can anybody guess what the highlight of me being in Cambridge is? Any guess? What do you think? Okay, a little bit. So it was the network of people I met in Cambridge. Okay, and that leads me to, apart from, there was a time I was like, oh, take pictures and all of that. That was when people started interacting. When you have an opportunity like this, don't miss it. One thing I never miss in Cambridge is when I attend an event, any single person I speak to, I connect with you on LinkedIn. If you're a student, you're not on LinkedIn, you're still far behind. Okay? So you can pull out your phone now, start downloading LinkedIn app and interacting. Then you are going to learn a whole lot. You have your Facebook for your social wherever, your Instagram for your videos and all of that. But LinkedIn is your professional platform where you get to look at what other people are doing professional and you get inspired. You build your profile and all of that. It's an amazing place. There are a whole lot of people who are in Nigeria who've been able to get some job abroad through LinkedIn. Because in there, all you need to do, you search what kind of internship, permanent role, temporary, whatever it is. And then it's able to, depending on location and requirements, you upload your CV. You can stay in the comfort of your home and you're able to get amazing job offer, whether part-time or whatever. So I think these are some of the things you need to continue building. And it's not enough to say, hey, Obina, please, can I have your LinkedIn? Can we connect? Right? What I also do is that once we connect, I go there and I chat you up immediately because I could forget where I met you. I'll say, hey, Obina, what's up? Just wanted to say, the conversation we had at Aodi event, that was really amazing. Thank you. Let's keep in touch. And that was it. Time came when I needed to make career decision of where next to go. It was those connections that I had to kind of reach out to, interact with them. Hey, I see you are working with this firm. Can we have a chat, maybe a Zoom call and all of that? And people are quite friendly and happy to, jump on calls with you and discuss stuff. Okay, so you are here, whether me, Alex, Nick, I saw some people trying to devil Nick where you're trying to take pictures. It's not just the picture. If possible, you can connect with Nick on LinkedIn. Someday you might want to come to Cambridge. It's easy for you to just, send him a chat there and say, hey, Nick, very interesting topic you taught on NMR and all of that. We're just connecting here to keep in touch if you don't know anything to say for now. In future, 2 months now, 1 year later, you might have something to tell him. And when you come back to say hi, he sees the previous charts you had. Say, oh, that was one of the students I spoke to in UNN. Okay, so building network and relationship, these are things you do consciously on your own. Don't just let it happen. You need to be strategic about how you do all of that, right? So please take this moment amongst yourself, exchange contacts, speak to folks from UK. Tomorrow, Bang and Alex are going to take the stage. Unfortunately, Ross is not able to join us, but he'll be joining us virtually. Ask questions, interact with them, exchange contacts, and all of that, okay? So I really, really strongly, not just with us, but amongst yourself as well, okay, build that network. Because when you leave school, when you leave uni, 3 years after I left school, like I still make posts on Facebook and someone comes, hey, Chooks Academy, thanks, you are the person, without you I wouldn't have passed my chemistry. I know some people might say, what's this guy saying? Yeah, the Chooks Academy you hear today, I know Michael is taking care of that, was actually my tutorial class. I found in that. Okay, so that's all of that. I think the main thing I'm trying to drive is the fact that, look, there's a whole lot of opportunity out there, but you need to go for them. They will come to you. And when you want to go for them, you need to be strategic about that. Okay? You need to plan yourself. I've spoken to a whole lot of people. There are a couple of guys I was speaking to there. They said we're in final year. And I say, what is life after final year going to be? And I think just one person told me he's got this idea that he want to use to change the world. But apart from that, others were like, we'll see what happens, right? But that's not the way it is. I think it's part of the reason from experience mentoring students from Nigeria to make application. We say that students are usually not thinking about 2 years, 3 years ahead of them until they get there. So an average Nigerian student wouldn't think about how would I in my first year, second year, even before getting to third year, strategically position myself to leverage and be able to capture opportunities when I graduate. These scholarships we are talking about, people want to see trends that you've shown. How have you shown some leadership during your first year, your second year? What have you done in the past to show that, yes, apart from the academic excellence, that if we sponsor you, you'll be able to do X, Y, Z. A lot of people, first class material apply to Cambridge. So you get to see that sometimes it's not all about your academic excellence. You need to then distinguish yourself because a lot of people has got that academic excellence. But for you to distinguish yourself, you need to plan ahead of time. In your first year, get involved with a whole lot of that. I think it's one of the things that we hope the campus ambassadors we are launching across universities in Nigeria, but we are launching it here tomorrow in UNN. It's one of the things we hope could bring us closer to students, to support students to think about, 5 years from now, what do I want to be? What are the opportunities I want to pursue? And how can I prepare myself, start to prepare myself from today so I can grab those opportunities when the time comes, okay? There is one software we've not sent you. Tomorrow, we are going to be using 2 softwares. One is AMBER for the molecular dynamics and molecular simulation, this docking thing and all that. Then the second is OCA, which is going to be used to simulate quantum dynamic things. Most of these things that Nick has been speaking about today, your UV, all of that, we can actually use computational methods to just simulate those things. So you don't even need to go to the lab to do that. Okay, that's the kind of thing I was doing. In my master's, I studied nanoscience of advanced metal complexes, investigating single molecule magnet that can be used for quantum computing. And I figured out that there are certain things which the experimental results we have could not explain. So I decided to go to Cambridge to then use computational techniques to simulate the world of those single molecule magnets. The idea is to see if there is a way we can increase the temperature at which that quantum phenomenon is usually observed, okay? So I never entered a wet lab in Cambridge. The computer was my laboratory, okay? I could sit in the comfort of my room and they just SSH into the departmental supercomputer or wherever and run, submit calculation, go to bed. Tomorrow, just grab the results, look at them, plot find and all of that, and that was it. So computational technique is an amazing way of trying to simplify the things you do. And I thought that this could help, propel the research we do here forward. But instead of you thinking, how can I combine A and B to get C? Would it actually work? You can actually use computation to see if such a reaction pathway is even possible, using the energy landscape and all of that. So you don't need to waste money buying chemicals and all of that. You use your computation to simulate what you're trying to do. And if it's promising, then you can spend that extra money because here another problem is there's no research fund. lecturers, researchers, final year students, master students use their own personal money to buy chemicals to do research. Throughout my master's, my PhD, I never spent a dime of my money in research. I get stipend and all of that. So I feel you, I understand what is happening here, which is the reason we're trying to see how we can better support. Okay. So I hope tomorrow, all of you are coming with your laptops. We've sent you a link for the Amber, but we are going to send a pre-read for the ORCA that we have the ORCA installation guide. So please, if possible, try to download that before coming to, so we can have a very easy and stress-free session tomorrow. Yeah, I think that is it. Drew, is there any other thing we need to remind you? Yeah, time 8:30. We are starting 8:30. Okay. All right. Is there any other question? Interaction from you? Yes, true. So because there's going to be a lot of laptops tomorrow, please, we have a few cable and board that we are able to draw light out. But if you can bring your own extension so you can draw them and disseminate them across, please. That would be really appreciated if you can do that.
Thank you. Thank you very much, Aodi. Thank you. Thank you so much. Please put your hands together. It's been a very long day and it's been my pleasure to be your host. Please, tomorrow, entrance will only be with your tag. Don't throw it away, don't lose it. You have to wear it to enter the hall tomorrow. Please, let's be here on time so we can get as much as we can from them before they go. Thank you so much. Have a good evening.
Thank you.